So next we are going to implement a sampling technique called top case sampling. So here we are not going to implement all the possible sampling techniques because yeah, that would be a book by itself. So I was only focusing on a few popular ones that give you the intuition of how sampling works, like the temperature sampling and the top case sampling, and they are also both relatively frequently used in LLM applications. There's another technique that is very popular, for example, top P sampling. It's not going to be covered, but yeah, I briefly discussed it in my other book, the Machine Learning Q&AI book. But top K sampling is a nice technique that we can combine with a temperature sampling, as I will show you in the next section. But by itself, let's briefly discuss what temperature sampling means. So I should have a nice figure here somewhere, I hope, in section 5.3.2. So here, that's the illustration of top case sampling in a figure. So if we have, again, our small vocabulary just consisting of 9 tokens with the index position shown below the token strings. So suppose we have the logits. These are the next token logits we worked with previously in the previous section. And now top K sampling selects the top K largest logits. It's quite intuitive, like the name says, top K. What are the top K highest logits? And here, for example, if we set K to 3, it will focus on the 3 most likely tokens or logits. So on the 0, the 3, and the 7 in this case. And what we will do is kind of similar to what we have done when we created the causal mask. So we will replace all the values we are not interested in by -infinity. And then we will apply the softmax. And what the softmax will do is it will rescale this. So again, that everything sums up to 1, but the -inf gets replaced by a 0. This is similar to what we have done in the causal mask. But now we are applying this here to the logits and for the token generation. And and why is this useful? So the reason why it's useful is in this case, we can make sure that the LLM will never generate, even with low probability, it will never generate any tokens that are not the top K token. So it helps a bit minimizing like the chance that LLM generates complete nonsense because we completely eliminate unlikely tokens. But then also, of course, it limits a bit the creativity of the LLM. It's kind of like a trade-off. 3 is just an arbitrary example. It's a hyperparameter. In reality, you might set that to 50 or to 100, 500, because in reality, we are working with larger vocabulary. Here we only have 9 tokens, and our real vocabulary is 50,257. But yeah, let's just see this in action, how this actually works. So let me just copy the next token probabilities or logits that we had here. We just redefine them so we have them here to look at. And then what we can do is we can define top K as 3 to mimic what we have seen in the figure. And then there is actually a PyTorch function. It's called top K. And for that, we can provide the next token logits and then the top K, how many we want. And so this will return 2 things. So this will return here the top logits. So the highest logits found here. So this would be 6.75, 6.28, and 4.5 here. So you can see it's also sorted by magnitude, which is quite nice. It's convenient. So let's give that names. Let's give it top logits and top position as the variable names. And yeah, so it's already sorting them for us. I can maybe just print them again here. So we have them. The next thing is now we want to set everything else to -infinity, right? So we have the next token logits. Oops. Here. And what we want to do is we want to keep this one, and this one, and set everything else to -infinity. So there are multiple ways we can do that. One way is, if we create these new logits with the -infinity values, is to use the torch.logit where function. So how does this work? So this accepts a condition. And so for the condition, we can say, for example, everywhere where the token logits are smaller. What's nice is actually this is sorted, where they are smaller than the smallest of these top logits. So saying here is if we look at -1, this should be the lowest one, right? So this is the lowest one in here. And we say everywhere where this is true. So here, everywhere where we have a logit that is smaller than this value, we have this condition true. And then what we do is we define an input and say everywhere where this is true, we say tensor float -inf. And otherwise we say just we keep the original value. Okay, so here we can't just say something like 1 or a torch tensor 1, because then everything will be either -infinity or 1. Here we provide the input token logits again, so it can take what it needs from that tensor. So again, so what we are doing is we are replacing the true values with input, and input in this case is -infinity. So these will get replaced with -infinity, and the false values will be replaced by whatever is found in the original tensor. So let's actually see if that works. I forgot a comma somewhere here. And yeah, so what we have now, let me clean this up. What we have now is our new logits, where we have the highest top 3 logits kept here, and then the -infinity. And yeah, remember how we used the softmax to apply this to the logits when we created the causal mask. We can do the same thing here. And since we only have one dimension, this will create this new tensor. And here, yeah, we can now have the probabilities here in a rescaled fashion, where we have 57% for the 0, 1, 2, 3 for the third position, and so forth. So here, this is one way we can zero out other probabilities. It's kind of related to what we are seeing here with the temperature scaling, where some of them get a higher probability when we set the temperature to a smaller value. But here we are more explicitly controlling how many tokens we want to keep or consider when we sample the next token. Okay, so now we have introduced 2 topics, temperature scaling and top K sampling. And so in the next section, I want to actually combine those to update our generate text simple function that we implemented earlier in this chapter.
Get this book at manning.com.